Thank you very much. So we will. I think we were trying to find now criteria for proving that spectral measures of unimodular random graphs criterion for spectral measures to be have a continuous part. So I think I quoted this paragraph, some positive answers. I will give you some recent results, and then I will prove some of them today. And next time we will speak about another topic if I am not too slow. Okay, so it's statement about what I used to call average quantum percolation, which is the problem of the existence of a continuous part or absolutely continuous part in the spectral measure, okay, where I recall you that if GO is a unimodular random graph, unimodular random rotated graph with low rho, we have said mu rho, the spectral measure, is the expectation of the spectral measure at vector a direct mass at the root for the adjacency operator. Okay. So our first result was the result which I quoted yesterday, was a result with Sen and Virag, which was saying that if you were doing band percolation, you look at percolation on Z2, and you look at this random graphs where you take infinite square lattice and you keep each edge with probability p and you root it at the root, at the origin. Okay. So there is the classical percolation criterion, which is called PC. Okay, which is such that if p is less than PC, there is the collected component of the origin is finite. So our result is it automatically implies that the spectral measure of that is pure point, purely atomic. So this is easy, but we can put also, and if P is larger than PC, then as this spectral measure has some non-trivial continuous part. Non-trivial continuous part. Okay, so in other words, it means that you can detect the percolation, the transition of classical percolation by just looking at the eigenvalues, and you will see some smoothness which arrives as soon as you are above the critical percolation threshold. Okay, so a second criterion result I would like to tell you is about random rotated trees. Okay, so first of that I should define what is a weighted graph. So we already saw that. So imagine that you have a weighted graph. Okay, so it's a graph, and you put some weights on the. So here my weights will be on the edges, and there will be 0 or 1. Okay, so it's a weighted. It's a kind of weighted graphs. Okay, where you just. So if this is my graph, you can represent the weighted graph. Is finally, if the weights are just taking value 0 or 1, it's just if I put in orange what is when the weight is 0 is 1, what you get is simply a subset of the edges, right? Okay, so you will say that a weighted graph is an invariant, is a line ensemble. A weighted graph is here. A weighted graph is a line ensemble. Okay, if for any vertex x, if you look at the sum of W x, y, where y is neighbor of x, so it's an edge of the graph, this belongs to 0 or 2. Okay, so we call that a line ensemble because it means that you can represent this by a union of disjoint lines. Okay, because it's if it's 0 or 2, maybe a picture. For example, you could make a line ensemble would be, for example, this graph here. If I put to 1 these three edges, and the rest is 0, this defines a line ensemble because for any vertex, if I sum the number of edges which I keep in my lines, in my ensemble, it's summed to 2 if I am on a line, or 0 if I am not. Okay. So this defines a line ensemble, and we will say that if the graph, if my graph is unimodular, if GO is unimodular, L is an invariant line ensemble, is an invariant line ensemble, called ELE for simplicity, if it is a line ensemble, if the weighted graph, when I add the weights, is unimodular. Okay. Maybe I could recall you the definition of unimodularity. So I mentioned only unimodularity for graphs, not for weighted graphs, but it's exactly the same definition. I recall you that what you should have when you have a unimodular object or graph, so this could be a weighted graph if you want, is a sum, if you take for any function which is non-negative and it's doubly invariant, the sum over all vertices of the function taken at the root the sum of the function, the expectation of the, you can think of this function as a mass sent on the network from a vertex to another. The sum of the mass that the root sends to the rest of the network should be equal, on average, to the sum of the mass that the network receives. Okay, this is the definition of unimodularity. So this should satisfy this for any such function f. Okay, so what we have proved with the same author, Bordenave, Sen and Virag, what we have proved is the fact that for any lambda in R, the mass, so rho, is a law of a unimodular tree, unimodular random tree, random rooted tree. So it's not a general statement. It only works if the support of the graph is supported on trees. Okay, so it's a big restriction, but still we have seen that in important examples such as Erdős-Rényi random graphs or many or the configuration model or graph with random graphs with different degree sequences were converging to trees. So it's still an interesting result. Says that the mass that the average spectral measure put on atom lambda is bounded by the probability that 0 is not in a line ensemble. So let L be an invariant line ensemble. So you look at the probability that the root is not in your line ensemble, and you count times the mass of lambda at rho prime, where rho prime is a law of TO condition on O not in L. Okay. So it means, this formula means that you can bound the mass of an atom okay, by the mass of the atom when you restrict to the condition that the root is not in the line ensemble. So there will be no atoms in the line ensemble. This is what you could try to remember. Okay, so it's fairly it's possible as a corollary, which I will not prove, but as a corollary, we could prove a result like that under the same assumption that there exists a line ensemble. It's not a corollary, it's let's say a lemma. Okay, maybe in particular, maybe I could first I will conclude the theorem. In particular, if you sum over all lambda, the total mass of atoms, mu rho, if you look at the pure point part, okay, I should write it in the other sense. If you look at the pure point part, the total mass of atoms, okay, is bounded by the probability that the root is not in your line ensemble. Okay. If you sum this inequality over all possible values of lambda, since mu of rho prime is a probability measure, it will sum to 1 and you obtain this formula. So as soon as you have an invariant line ensemble with a positive density, meaning that the probability that the root is in the line ensemble is positive, then you have some continuous part of the spectral measure. So the continuous part is at least the probability that the root is in R. Okay, so and we have a lemma, which I will not prove, is that there exists a line ensemble with the same assumption, such that the probability that you are in L is at least 1/6 times as soon as the degrees, in terms of the regularity of the degrees, divided by, we have many more criteria, but it's just. Okay, so with this lemma, we could prove, so it's relatively easy to construct invariant line ensemble on random rooted trees, as soon as the degrees are not too wild, meaning that they have a finite second moment. And in particular, we could prove the following result, which is exactly the same. If you take a unimodular Gretton-Watson tree with probability distribution pi, okay, and pi is different to a direct mass at 2, then mu rho contains a non-trivial continuous part, non-trivial continuous part, if and only if what I could call, so you have pi, which is a description of the root, and then the other offsprings have a distribution pi hat, which is a size biased of pi. Okay, normalized. Of course, you should have assumed that you have finite first moment for that. Okay, so and let's call the average of pi at mu hat. Okay, so of course you can write it in terms of the average of pi. And what we have as a corollary is that as soon as the average, as soon as the mean number of offsprings has an expectation larger than 1, then you are continuous part. And if it's not the case, then you have your pure point. Okay, so this is exactly the same result. This is exactly the same result than this one on percolation, saying that you will have existence of a continuous part as soon as you have an infinite connected component. Okay, so this, because the classical percolation, this corresponds exactly. Maybe we call that the probability under rho that under unimodular Gaussian tree with probability pi, degree pi, that the tree is infinite. Okay, the connected component of the root is infinite, is positive. This is equivalent to that, positive. Okay, and let's say that pi is different from that. Okay, so we have a criterion which says that you will have continuous part, a continuous, non-trivial continuous part, as soon as you have you are supercritical. Okay, so that's very neat. Maybe yes. Okay. We don't know some open problem. We don't know whether or not this is sharp or not. So open problem. Is it true for trees that the total mass of the pure point part is it equal to the infimum over all invariant line ensemble E of the probability, the supremum, sorry, no, the infimum of the probability that 0 is not in R. Okay, this we don't know if it's true. It would be very nice because it would give a very nice. If it's true, it would give a very nice geometric interpretation of atoms on random wanted trees. We still have one born, which is good, but it could be nice to have a more complete description.
Can I ask?
Sure.
So in this corollary, so do you know the location of the continuous part? I mean the
location. Yeah. Okay. So we know something. For example, here. So it says that we have some toy example where we know more or less where is this continuum. We know where the atoms cannot be due to this relation. Okay, yes. Because this relation tells you that you can only have atoms where you can only have atoms in places where you have an atoms for the unimodular tree where you have removed this line ensemble. So, for example, in the example we make in the paper with Balin Spirag and Arnapsen, we make a toy example where we call that stretched. We take a stretched trees. We start with a two regular tree, and then we put with a three regular tree, and then we add some, for example, so according to some distribution, we add some edges on the lines. Okay, we extend one edge to put extra edges. Yes. So if you apply our result, you will deduce that there exists a line ensemble which covers all vertices. Okay, so there exists an invariant line ensemble which covers all vertices. Okay, so something like that. So the only thing which will be remaining, which would be the only place for rho prime, it's rho prime will be the union of such string. So we deduce from this toy model that the support we deduce from this toy model that the support of the pure point part of this must be included in the interval -2, because it has to be the atoms of a line, which you already saw as being these two cosine. But we also know that the support of mu rho, for example, it could be is equal to, if you take the choice, will be equal to the same support than the contained and is strictly different from -2. So we know that there at the edge, so there could be some atoms here, but the spectral measure is something here, and we know for sure that here it's continuous.
I see.
It's a toy model, so But no, it's a good question. We don't know. And also we don't know what about absolutely continuous part. A geometric criterion for absolutely continuous part is missing.
I see.
There is one result though in this direction, which is a recent result of cost of Sales, cost and Sales. Which says that you remember we had a result on we had a result I mentioned the last time, a result on the mass at 0. So we had a paper with Justin Sales and Marc Lelarge where we computed the max. We have computed for unimodular Galton-Watson tree. So this was in a previous paper. We have computed the explicit formula for the atom at 0 of a unimodular Galton-Watson tree. But Justin and Simon Coste have managed to have a refinement of that on the existence of something related to the absolutely continuous part. They have computed the limit as lambda goes to 0. You look at the number, the mass between minus lambda and lambda, and 0, you divide by 2 lambda, and you would like to prove that this is 0 and positive, and they say essentially that this will be positive if the maximizer, so this is M of X star, okay, there is a maximizer, if X star is a unique maximizer. No, it will be 0 if X star is a unique maximizer. And if not, if X star, if not, if two maximizers are them. Okay, so here they have also to assume that M7 of X star, I think, is negative, but okay, it's a detail. Okay, so there is some result on absolutely continuous part, but just restricted to at 0. Okay, which is okay. So so I will try to give you a proof of this theorem and maybe the theorem on percolation. Maybe quickly, I want to give you a final result on quantum percolation, because this was a result for the what I call average quantum percolation. So in quantum percolation, you want to study the regularity of the spectral measure at the root. This is a random probability measure. Now you don't want to take the average, and you want to study the regularity of this measure. So this is what motivates the most physicists. And on trees, there have been some progress recently, which I will comment. So this is a recent paper with a PhD student of mine, which says the following. Okay. So you take a rho, which will be, okay, for simplicity, I will take a Galton-Watson tree with offspring distribution pi. Okay, not unimodular, but it's the same statement. It's just something more complicated to state. Okay, so here the root has low pi and everybody has low pi. Okay, this is the usual Galton-Watson tree. Okay, you assume that pi 0, so the mass that this probability measure puts at 0 is time. Okay, to put D to be the expectation of n, where n has low pi. Okay, and you assume that pi 0 because as soon as pi 0 is positive, as we have seen, there are atoms everywhere in the spectrum, okay? But you assume that pi 0 times d is bounded by a universal constant. I forgot to 4 maybe, or, okay. C0 is a universal constant, okay? Okay, now there are two statements. The first is if for any epsilon positive, there exists a constant C epsilon, which is strictly larger than 1, such that if the expectation, so this is a measure of the relative variance plus 0 and power 5 or 6, 12, is bounded by C epsilon, then condition on non-extinction, because your tree can, as soon as pi 0 is positive, your tree can be, the tree could have, could be finite with positive probability, okay? Then condition on non-extinction, mu G as is as a non-trivial. So this is a random as a non-trivial, as almost surely a non-trivial absolutely component. And the expectation of this mass the absolutely continuous part is at least 1 minus epsilon. Okay, so as soon as the variance, the relative variance, because this is the expectation, so as soon as n over d, sorry, c plus should be, if it's 1, so it's 1 plus. Maybe, but right. So this is at least sorry, so 12. So it's ugly. Maybe what? How could I write it? Okay. Okay, I think 2 let's write it like that. Okay, so this is an n over, so if n is equal to d almost surely, then this will be equal to 2. You subtract 2, would you subtract 2, so this will be equal to 0. So as soon as, so this is a measure of the concentration of the offspring distribution. This is a measure of the offspring distribution with respect to its average. Okay, so as soon as it's the relative variance is small enough, you will have an absolutely continuous part. And if you assume, so this is, and if you assume that that there is no leaves, that P0 is 0, okay, so the tree has no, is infinite with probability 1, then you have a refinement of that, because in this setting, if there are leaves, we know, for example, that it could be that there are atoms, this measure as atoms with probability at all totally real algebraic integers, so on a dense set, on a dense subset of R. But this happens as soon as you have many finite pending subtrees, as we have seen. But if there is no tree, no such finite pending tree, so if it means in this setting that pi 0 is 0, okay, then moreover, so you can apply, of course, this criterion for any e in -2, 2. You can find there exists a new constant C prime of E, which will be positive, such that if the relative variance So I think here it's you just have to take moment power 5 or 6 is less than C prime of P, then mu G is almost surely absolutely continuous on the interval 2 minus square root D minus E square root. Okay. So in the second case, when there are no leaves, we can guarantee the fact that there is an interval where you have no atoms. Okay. So in particular, this applies to the let's call that I, and this to I applies to unimodular greater than 3 with Poisson offspring distribution D for D larger than D of epsilon. Okay, so it means that because the relative variance, if you take n to be Poisson, a Poisson random variable, if n is Poisson, n over D is of order 1 over square root D with high probability. Okay, so it will concentrate for D large enough. So if this criterion for any epsilon, you'll be able to apply it. So even if we know that this spectral measure has atoms at all totally real algebraic integer, we can prove that if D is large enough, there is this times actual quantum percolation, meaning that this random measure has an absolutely continuous part. Okay, so in particular, it also implies, as I said, if you have quantum percolation, it implies it's stronger than average quantum percolation, so it also implies the existence of an absolutely continuous part in this setting. It leaves open the criterion of what is the threshold. Open question. What is the threshold of quantum percolation? What does it mean? What is the smallest D? Smallest D positive, such it will be larger than 1, such that if you look at the unimodular pattern with Poisson D, you root it as a non-trivial AC part with positive probability. With probability positive. Okay. This is open. We don't know. There are some conjectures. The physicist made some conjectures. There are two values. D equal to E is a good candidate, or D is 1.42. We don't know. Okay. So I hope that I will, at the end of this lecture, of today's lecture, I will give you some. I will try to explain you how you can deduce from this quantum percolation results, how to deduce results on finite graphs with convergence in the Benjamini-Schramm sense to these objects. Okay. But first, I would like to prove.
Excuse me.
Yes.
Can I interrupt you and have a question?
Sure.
On the second statement of this theorem, you are saying you have a AC component on this interval from minus E square root of D to E square root of D.
Yes.
Are you saying that AC component contains this interval, or?
Yes.
Yes. So this interval belongs to the AC component. This is okay.
Yes.
Thank you.
And there is no atoms here.
I mean, this interval is contained by the spectra.
Yes.
Okay.
Yeah. Sorry. Yeah. It has absolutely and positive density, and this measure.
I mean, some sort of spectra contains this.
As an almost everywhere positive density.
Okay. So there's no spectral gap on this interval.
No.
Okay, I see. Thank you.
Yes, it's a good question.
Yes.
Yeah, we also prove that there is, there is it's purely absolutely continuous on this interval, and the resonance density is almost everywhere positive.
Thanks.
Yeah, good question. Okay, so so this result, as you can see it from the statement, is looks much more technical than the results on the average quantum percolation. So I will. So there are obviously more. It's more difficult to. It's less suited for a course to lecture to explain the proof. So I will probably not mention the proof of this result, but I will give you the proofs for the criterion of a continuous part for the average quantum percolation problem. Okay. So first, I will give you two tools. The two tools I know for bounding eigenvalues multiplicity. Bounding eigenvalues multiplicity. Okay. So the first method that we have used with Sen and Benjamini-Schramm is a method which we called monotone labeling. Which is relatively easy to introduce. So a labeling is simply, so we take G to be a graph, not necessarily finite, and eta, a labeling is simply, it's simply a function from the vertex set to the integers. Okay, so you just give a number. To each vertices. Okay, so now once that you have your labeling, we split the vertices in three categories. We say that V is a prodigy. If it has a neighbor, if there is this W which is connected to V, okay, which is different from V, I should say, with label which is strictly less than the label of V, and for all vertices neighbor of W, different from V, eta of U is less than eta of V. Okay, so V is a prodigy if it has a neighbor such that all around this neighbor, the labels are strictly below the value of V. Okay, we say that V is level if it is a local maximum for the labels, if for all W connected to V, eta of W is less or equal than eta of V. Okay, and not if it's V is level, if it's not prodigy and not prodigy. And V is bad otherwise. Okay, so we have for every labeling of the vertices, we partition the vertices in three categories. Okay, so this definition suggests that we would like to have many prodigies, a few level, and few bad vertices. Okay, so just to, I will give you an example. Okay, so as you say, it's the same example that you can find on our paper, so I will produce it because I'm sure that I will not make a mistake. Okay, this is my graph. Now I give you the label. So this one receive label 2, this one label 2, this one label 4, this one label 2, this one label 3, this one label 3, and this one label 1. Okay. Now let's try to find the bad vertices, or the easiest one we can make them in red. So which one is bad? No, maybe next, it's easier to find the prodigy, maybe. Let's put them in red. Let's see. 4, maybe 4 is a good candidate. So it has a neighbor which has this label 2, and all neighbors of this guy have label 2, 3, and 4, and it's strictly less than 4. So this one is a prodigy. Okay. And 3, it will also work for this guy because 3 has a label as one of his neighbor, 1, and 1 has one neighbor with label 2, and what? Okay, so this guy is a prodigy. So if you browse, you will see that this is the only example. And now for level, let's call them I don't know, orange. The level vertices, it's relatively easy. They should be local maximum. So this is not the case. This is the case. So this is a level vertex. This is not the case. And this is also the case. So these two are level vertices, and the two others, they are bad. You can put them in green. So this one is bad. This one is bad. And this one is bad. Ah. Okay. Okay, so now that I will give you this criterion first for finite graphs. Okay, so let G be a finite graph. And eta be a labeling. Eta a labeling. Okay. Let's call with L level vertices and B bad vertices. Okay. And the statement says that for any eigenvalue, let's say lambda with multiplicity m, multiplicity n, we have the multiplicity, so the dimension of so m is the dimension of k of a minus lambda I, okay. We have m less than the number of bad vertices plus the sum over all j of Lj, where Lj is the multiplicity, maybe I could write it like that. I don't have the place here where Lj is the dimension, is a multiplicity of the eigenvalue level j of the eigenvalue lambda when you restrict to vertices which have label j. Okay? So this is the formula which bounds the multiplicity of an eigenvalue. Okay, so in particular, if you sum for any k, if you sum k multiplicities, it will be less than kb plus l. Okay. So this is an interesting formula. I will first give the proof. and then make some explanation. So in some sense, first prove that this term implies that. What is it in particular? Because if you sum over multiplicities, okay, so the sum, let's call if Lj of lambda, if Lj of lambda is a dimension of I write explicitly the dependence in the eigenvalue. Okay. If you and m of lambda is a dimension of the kernel A minus lambda, okay, you have that if you sum the multiplicities of any eigenvalue, this will be less than if you sum KB, if you apply this inequality, plus the sum of Lj of m of L of lambda Lj. So you sum over going 1 to k of Lj of lambda k. Okay, but this sum by assumption is less than lambda Lj. Okay, because the sum of the multiplicity of eigenvalues is less than the dimension of the number of level j vertices obviously. Okay, so that's why, and the sum of lambda j, which is then equal to kb, the sum of the lambda j is equal to L by assumption. Okay. So I didn't define what is Lj, sorry, which is equal to the maybe total number of level j vertices. Okay, so this proves the in particular part. So let's prove the theorem. Okay, so Lj is a multiplicity of the eigenvalue lambda for level j vertices, and b is the number of bad vertices, and m the multiplicity of the eigenvalue. Okay, so the idea of the proof is that this labeling will give you an order, since it will give you an order in which you solve the eigenvalue equation. Okay, so let's E to be the eigenspace of eigenvalue lambda vectors. Okay. Okay, so by assumption, the dimension of this space is M. Let's say B is the vector space of vectors which vanish at bad vertices. Okay, so vectors which vanishing on bad vertices. Okay, so there are the vectors which are 0 on bad vertices. So the dimension, the codimension of B, which is n, let's assume that cardinal of B is n. The codimension of B, which is n minus the dimension of B, is the dimension of the orthogonal of B, which is B. Okay. Let Lj be the set of level j vertices. Level j vertices. Okay, so the dimension of okay, and Ej will be the dimension of K of are the eigenvectors of restricted to lambda j. Okay, so the dimension, what the assumption says that the dimension of Ej is Lj. Okay. So finally, we define the set of vectors, which are the set of eigenvectors, which are which vanish on bad vertices, and which are orthogonal to all of the Aj's. Okay, so you look at the vectors which are not an eigenvectors associated to any level j vertex, and which vanish on B. Okay, so the dimension of E prime I should recall you the codimension formula, which says that the dimension of A, if you have two vector space V and let's say A and B, the dimension of the intersection of A and B is at least the dimension of A minus the codimension of B. Okay, so if you apply this formula multiple times, you will find that the dimension of E prime is at least the dimension of E minus the codimension of B minus the sum of J of the codimension of EG orthogonal, which is equal to the dimension of E is M, the codimension of B is B, and minus the sum of J. The codimension of the orthogonal is simply the dimension of EJ of the LJ. Okay. So the lemma follows because if the theorem follows, we claim that E prime is 0. Okay. So if we prove that, once we have proved that E prime is 0, it will imply that the multiplicity, so if E prime is 0, this is 0. So you obtain the requested inequality on the multiplicity. Okay. So what we have to prove is that an eigenvector which vanish on bad vertices and which vanish on all, which is orthogonal to all these EJs, should be 0. Okay. Okay, so indeed you take F, a vector in E prime. You want to prove that F is 0. So we use the labeling by saying we prove this by induction. We prove that F is 0 by induction. Okay, so we assume that F, by proving that F vanish on LJ. Vanish on LJ, okay, by inductions from J increasing. Okay, so we will prove that we assume that F vanish on LJ, so we on Li maybe for all I less than J. So by assuming that F vanishes on all the Li's, yes, by proving that the vertex vanish on all the Li's, we will have proven that F is 0. Okay, so F of X is 0 if X is bad, of course. And we also prove that F will vanish on prodigies. Okay, but we'll not use that in the induction. Okay, so the first comment is that if V is a prodigy with label J. Okay, so we assume by induction that F, what we want to prove is that F is 0 on all vertices, that F is 0 on all vertices with label less than J, and do that by induction. So we assume that F is 0 for all vertices with label strictly less than J. Okay, so if it's a prodigy with label J, then by assumption there exists, so maybe on all, assume that on vertices with label I less than J. Okay. So by assumption, it means that there exists a vector W, which is neighbor of V, with label with label eta of W strictly less than J, and all vectors neighbor of W which are different from V have label different from strictly less than J. Okay, so in particular, from the induction hypothesis, maybe I can write it in yellow here. In particular, from the f of W is 0 and also the f of U. Okay. We write down, but f is an eigenvector because f belongs to E. Okay, so we write down the eigenvalue. We have that lambda is equal to the sum over all y neighbor of W of f of y, which is equal to f of V plus the sum over all U neighbor of W, U different from V of f of U. Okay, so by assumption, this is 0 because f of W is 0, and this is f of V plus 0 because this is 0. So f of V is 0. Okay, so we have proved that using our recursion assumption that f vanish exactly at all prodigies with label J. So you see how we use the definition. We use the definition of prodigy by just saying that by giving an order in the way we solve the eigenvector equation. Okay, now so I recall you that Lj are level J vertices. So the outer border of Lj, so which is the vertices which are neighbor to an element of Lj, but which are not level J vertices, this is included in the set of bad vertices union the level I vertices with I less than J, and union the prodigy with label J. Okay, why? Because if you have a level J vertices, you must be a local maximum. So you cannot have any vertex in your neighborhood which has label larger than J, larger or equal. So you can have it could be a prodigy, or it could be any other vertex with a label less than J. Okay, so this is so in particular we have proved that f restricted to delta label J of the boundary is 0 by the recursion hypothesis. Okay, so if you have a label, so it implies since f solves the eigenvector equation, it implies that f restricted to Lj is an eigenvector. Okay, because you have Lj, since you are 0 on its boundary, since you solve the eigenvalue equation, if you solve it and the boundary is 0, you will solve it exactly the eigenvector equation inside Lj. Okay, since your vector is null on the boundary. But this contradicts, it's not contradiction, but if but f belongs to what we called EG orthogonal. But you are orthogonal to any label J vertex eigenvector. So this implies that f is 0 on Lj. Because you are an eigenvector, but you are orthogonal to this space. So the intersection is 0. Okay, so this is the way you prove by induction the theorem. Okay, so we have proved that E prime is 0 by proving it for an increasing number of labels values. Okay, so the good point, maybe I will make an example. I will make an example which we call a vertical percolation. It's just for pedagogical purpose. So you imagine that your finite graph is a chunk of the grid. Okay, let's you put n1 to n here and 1 to n. No. Okay, and you take a subset of this grid, so you don't take you take all horizontal edges of Z2, but you just take a subset of the vertical edges, an arbitrary subset. Okay, we call that it's one graph. You could make that at random if you want. Okay, so let's put a label to a vertex xy. So x-axis, y-axis, just to be the value of x. Okay, so this guy receive label 1, this one label 2, this one label 3, and so on. And this guy receive label n. Okay, so now I claim that this guy is a prodigy because it has a neighbor 2, and all other neighbors of 2 have a label which is strictly less than 3. Okay, because this one and this one, they have a label which is strictly less than 3. Okay, so all these vertices here, they are all prodigies. Okay, and okay, is this one also a prodigy? It doesn't all other neighbors. Ah, okay, it works also here. Sorry, it works also here because 2 has a neighbor 1, and 1, the only remaining neighbor of 1 is this one, and has label less than 2. Okay, and these vertices here, so you can use green. These vertices here, they are bad. So there is no, in this case, there are no level vertices. So it implies that the multiplicity of any eigenvalue is bounded by the number of bad vertices, which is n. So if you come back, but there are n squared vertices. So if you look at the mass that you put on an eigenvalue, it is less than 1 over n, which goes to 0 as n goes to infinity. So if you do vertical percolation, you see the local weak limit cannot have atoms. Okay, so all atoms there will be no atoms. The limit measure must be continuous. Okay, so this is an example of vertical percolation. There is an extension to unimodular graphs of this criterion. To unimodular graphs, which is as follows. So because the criterion as I defined it was only for finite graphs, but okay, so you take a unimodular measure. So the fact that there is a criterion for unimodular graphs, so you look at M and tau, the associated von Neumann algebra. Von Neumann algebra with trace tau of an operator. So this is the algebra of random operators built that you can build on your graph, which does not depend on the specific choice of the root. If I should say it in loose words, and the algebra, the trace, sorry, is simply the expectation of the value of your operator, the diagonal entry of the operator taken at the root. So we have seen last time that this is defines a faithful trace and it's also a normal faithful trace. Okay, and when you have a, if P of S is an orthogonal projection, onto a closed vector space, okay, S, and P of S is an operator in norm. The fundamental dimension of S is defined as the trace of P of S, okay, which is so the expectation, the norm of the projection, the orthogonal projection of your root. Okay, so this is a fundamental dimension. Okay, so why I mention that, because when you are so in the previous proofs we have used like the codimension formulas and some formulas on dimension, but these formulas they extend for the fundamental dimension when you have a trace on your fundamental, when when your state is a trace. Okay, so it satisfies the codimension formula. Okay, so using that, we have the exact analog of our previous result. You take a unimodular graph, and eta an invariant labeling. So invariant labeling is as previously, it means that G eta O is unimodular. On integers, so eta is from V to Z on integer, and you defined L to be the probability that the root is level. So this is exactly the dimension. This is a fundamental dimension of the levels of the level sets of the level vertices. You look at B to be the fundamental dimension of the bad vertices. Level vertices. Oh, bad vertices. And Lj to be the dimension, the fundamental dimension of the kernel of A restricted to level J vertices minus lambda. Okay, so this is the same as before. Then for any lambda, the statement is that for any lambda, mu rho of lambda, rho is as usual the law of the rooted graph, mu rho, the mass of the atom, is bounded by B plus the sum over J of Lj. And consequently, in particular, mu rho of lambda, if you sum any k atoms, it will be less than kb plus r. So this is formally exactly the same, and the proof is the same, at least when you have bounded the same proof, because it's just that an increase of technicality because you are in this fundamental algebra setting, but since all inequalities that we have used are also true here, this is the same proof. Okay, so I don't mention that. And we used this theorem to prove the statement on the invariant line ensemble. Okay, so I will sketch the proof. So I will recall maybe what was that? Where was that? Yes, this one. Okay, so we have this result on the invariant line ensemble. And so what we do to prove that is we built an invariant, we use this criterion. Okay, so we have to build a labeling when we have an invariant line ensemble. So we sketch the proof. It's not. What we do is you have your tree. So your tree is is a whiteboard, and this is a line ensemble. Okay, you can represent it something like that. Okay, maybe in gray. So this is a line ensemble, so it's in black. Maybe in gray there are some. And the gray is not right, but okay. There are some finite trees around. Okay, so you have the picture, so they should be connected. Okay, these gray lines could be infinite. Huh? Okay, maybe I should write in red the line ensemble, it's better. Okay. Okay, so you have the line ensemble and you have the tree. Somewhere you have the root. Let's say here. Okay, so what you do is you can extend your probability space so that it remains invariant, but you put a direction, for example, by sampling ID cos, toin cos, you put a direction on the lines. Okay, so this way they can define a gradient. Okay, so you look at a function eta, which will be the labeling, which will be on the vertex of your tree to z over kz. And you want the discrete gradient, delta of eta, which is eta of you want the discrete gradient to be a function on oriented edges of uv to be eta u, eta v minus eta of u. So then you want this to be L of uv. Okay, so because the line ensemble, so where L of uv is 1 in this direction, it's -1 in the other direction, and when you take L of minus v between outside, it's just 0. Okay, so L of uv is equal to 1 if the oriented edge uv belongs to and 0 -1 if vu is in L and 0 otherwise. Okay, so you use this line ensemble to have a gradient. Okay, and you want to find a function eta, a labeling eta, whose gradient is exactly given by L, by these weights. Okay, so it means that it increases along the lines, it decreases in the other direction, and when you are outside of the line, it's constant. Okay, and since you want a gradient to be in 0 kz, there are exactly k such functions. Why is that? Because once you have chosen the label, for example, of the root, if the label of the root is, I don't know, 1, it means that here you will put 1 everywhere, and then you will put 1 here, here you will put 2 here, 3 here, -1 here, and so on. And here you will have a 1 here, and then you will have 2, 3, and so on. Okay, so there is a finite number of such labeling, and the number is k, and you take one at random. Eta, a uniform uniform K labeling. Okay, so and then your tree, this let eta be such a uniform K labeling, and eta is an invariant labeling. So you have to check that you, by doing this, you never use, in some sense, the position of the root, and you have built an invariant labeling. Okay, and when once you have built this invariant labeling, that's nice because maybe I will make a zoom. So here you are on the line. We got 0, 1, 2, 3, and then you come back to 0 if k equal to 4, 0, 1, okay, and so on. Okay, and there is also the finite pending, and here you have 0, 0, 0, 1, 1, 1, and so on. 2, 2, 2, okay. You can represent it like that, and what you will say that for this labeling, all these guys different from 1 and 2, they are labeled. These ones are prodigies. Okay, this one and this one, they could be bad. No. It's very difficult to see where the pencil is. Okay, so this one and this one, they are bad. And all the rest are level vertices. Okay, because the rest, they are all the neighbors by assumption they have the same label, so they are local, they are level vertices. This one could be bad, and the rest is prodigy. Okay, so that's why you use the lemma, you use this theorem, and you will arrive quite quickly to our result. Maybe I will stop here for this sketch of proof because time is going on. Okay, now I want to explain a second tool to prove to bound eigenvalue multiplicities, and this is a tool that we use to prove the statement on percolation on Z2. Okay, so I think we call that minimal path matching. Okay. Okay, call that MPM. It's long to write. Okay, so this is this criterion is we have been able to make something of it only for finite graphs, but it does not mean that there is a general version in this for all unimodular Cauchy graphs. So you take a finite graph and you take two sets I1 up to IB, J1 up to JB of let's say, at the intersection. So it's two disjoint subsets which have the same cardinality, B. Okay, so I use the letter B because it will remember use the bad vertices of the previous tool. Okay, so a path matching pi, it's a collection of B paths from I to J. So a path matching from I to J. So it's a collection from B, it's a collection of self-avoiding paths. So Pi are paths in the graph. Okay, so they are vertex disjoints. Okay, so pi1 is a collection of, so you have somewhere here I. Somewhere here you have J, 5 points, B equal to 5. And I want to find 5 paths which are vertex disjoint. Okay, I have added 2. Okay, and so there are my paths. So this will be pi1. This will be pi1, pi2, and so on. Pi3 and pi4. Okay, so the path pi L is goes from is UL1 up to ULPL. Okay, well, PL is the length of this path. UL1 is equal to I L. Okay, and ULPL is equal to J of sigma L, where J is a permutation, where sigma is a permutation on B elements, okay, which we call the matching map. Okay, and so the length of pi is defined as the total number of visited vertices. So this is the sum from L1 to B of the length of pi L, which is the sum from L1 to B of the PL. Okay, so this is the length of pi. Okay, so if I have a notion of length, I have a notion of now minimal path matching. Pi is a minimal path matching from I to J if its length is minimal. Is minimal over all path matching from I to J. Path matchings, yes, from I to J. Okay, so yes, so we have these collections of paths, and when we, so it's the same way that you see with this criterion of invariant line ensemble, when we have long lines, okay, we prove that when you have lines, this by infinite lines, or this or these long line segments, it restricts it tends to create some continuous spectrum. Okay, here we will do the same, and the idea is the same. When you have this disjoint collection of lines, okay, then you will have some continuous spectrum, or at least some bounds on the multiplicity of eigenvalues. And here is a proof. Here is a theorem. Okay, so maybe we put credits after that. The finite graph. Okay, so I and J are two as above. Okay, disjoint. There is an assumption that assume that all minimal path matchings have the same matching map. Okay, so they could be, we assume that there could be multiple ways to go from I to J with a minimal number of steps, but by doing so, you don't use, the matching maps are always the same. Okay, so if this is true, so for example, it's true if there is a unique minimal matching map. Then we have the following statement that if cardinal of V minus L is the length of a minimal path matching map from I to J, then if you sum over all eigenvalues multiplicities. You subtract b, you take the positive part, it's less than I, okay? Where M1 and R are the eigenvalues multiplicities. Okay, so you have R distinct eigenvalues, and X plus is simply the maximum, the positive part. So in particular, if for any k, M1, if you sum k eigenvalues, this will be less than kb plus L. Okay, so formally it's the same inequalities that for the monotone labeling, but with a slightly different concept. Okay, so we have an assumption which is crucial, because here it is crucial, and notably you will see that this is crucial because, for example, this assumption fails when you try to apply this criterion for the Lamplighter group. And we have seen that for the Lamplighter group, the spectrum could be a pure point, okay? So that the multiplicities are big. Okay, so just to check, how do you, if you come back to this vertical percolation, okay, where you just take a subsample of vertical edges. Here you have 1, n, and also n. Okay, the multiplicity of an edge, you could say, you could fix I to be this left part. Let's say that this is I with cardinal b equal to n. This is j, okay. And of course, there is obvious minimal path matching, which is just the straight lines. Okay. So it is unique. And so in this setting, the number of paths that you take is b equal to small n. Okay. And the number of leftover vertices, L is 0. Okay, because V minus L is the length of the minimal path matching. So here the length of the minimal path matching is n squared. All vertices are used. So it implies that the multiplicity of any eigenvalue is bounded by B, is bounded by n. Okay? And this is exactly the same result that we have seen with the other criteria. Okay, so now, so this proof of this theorem, the first, there was a paper by Kim and Shader, which use a kind of criterion like this one for trees. And so we extended the idea of their proof to this general framework in this paper with Sen and Virac. Okay. So let's keep the proof. So the proof is based on what is called the Smith normal forms, or the divisibility property of the characteristic polynomial of subgraphs. Okay, so it has nothing to do with, I should have mentioned that for the invariant labeling technique also, the monotone labeling technique. You don't really use the fact that you are dealing with the adjacency operator. It could be, it could work for weights different from 1. We never use the fact that the weights were integer. So here we will, okay, so it's also a kind of general statement. So yes, I will try to prove that. So you take two subsets of, for any two subsets of the vertices, you consider A minus Xij, okay, to be the okay, maybe I will go directly to if B, no, A minus Xij to be the matrix A minus X with rows I and columns J removed. Okay, so my convention is not usual. What the subscript is for the rows and columns I remove, not that I keep. Okay, so they have the same cardinality. And then I define Pij of A to be the characteristic polynomial of this matrix. Okay, so it's a polynomial. And we introduce for a given set, for a given integer b, the greatest common divisor in the ring of polynomials of all Pij of A, okay, where you remove any number of vertices of rows with cardinal b. Okay, so the greatest common divisor is by convention a monic polynomial. Okay, it is a monic polynomial. It is a monic polynomial. Okay, and maybe I should recall before going into the proof that any polynomial divides the zero polynomial. Okay. Okay, so and note also that the degree of Pii of A, so it's a characteristic polynomial when you take a subblock, you just remove the rows and columns of I. This is a characteristic polynomial of a usual matrix. So this is a degree. The degree of this polynomial is n minus b. Okay, let's assume that cardinal b is n. Okay, so in particular, the degree of delta b of A is bounded by n minus b. Okay, so the goal of the proof will be to try two places. We will relate the degree of delta b of A of the degree of this polynomial delta b in terms of the multiplicities of eigenvalues. Okay, and then we will prove by choosing carefully I and j in terms of fast matching, of course. We will prove that the degree should be much less than n minus b. This is what will give the improvement on which will get what will give our eigenvalues multiplicity bound. Okay, so the first part is to try to, when you have a symmetric matrix, matrix with eigenvalues, with distinct eigenvalues. Well, when you have a symmetric matrix with distinct eigenvalues, lambda 1, lambda r, with multiplicities m1 and r. Okay, so there is an explicit form for this monic polynomial. It's simply the product of x minus lambda I power mi minus b plus I onto r. And in particular, we are only interested in the degree of this polynomial. The sum of the degree of this polynomial delta b of A is equal to the sum over all eigenvalues multiplicities of the mi minus b plus. Okay. So you see, we are getting closer to the statement of the theorem. because the statement of the theorem is about the sum of the mi minus b plus less than something. Okay, so what we will do is we will find a non-trivial polynomial of which will be based on these path matchings, which will give an upper bound on this the degree of this greatest common divisor of all characteristic polynomial of minors. Okay, so the proof of this theorem of this lemma is I guess a classical proof. So if you so the cardinal of the vertex set is n, so it is nothing. It's a general result for any symmetric matrix. If you have a polynomial b, you take a polynomial b in the ring in the matrix values. So you take a matrix values. You take a polynomial valued matrices. Okay, so each entry is a polynomial. Okay, so then you defined Pij of b exactly as we did. This is a determinant of b when you remove the rows I and j. Then you define again delta b of matrix valued polynomial as being the greatest common divisor of all Pij b with I cardinal of I equal to cardinal of j is equal to b. Okay, so we retrieve our previous definition. Delta b of a minus x is equal to our previous notation. Our previous notation. Okay, so I changed slightly the definition. So I extend it to not only a minus x, but to any polynomial valued matrices. So the first thing is that if you take, if you observe that if you take W11 of B1, if you look at the determinants, okay, and I make on the first row, column, sorry, I make a linear combination of the columns. So let's write B of x as being the first column, the second column, and okay, so it's m columns. And for at the first row, I make a linear combination of all the others. And I restrict that to ij. Okay, so if if one is not in J, okay, so it means that we keep one is one of the columns that we keep because one is not in J. So I can use a multi-line linearity of the determinants, and this will be the sum from J1 to n of W1J of determinant of Bj, B2, Bn. Okay. And by definition, adjacency. And by definition, this will be divisible by is divisible. So if J is in if J is in J, if J is in J, is 0. If J is not in J, you can switch it. You by using the multiplicarity of the determinant. That's why that you can switch columns and up to minus sign. We find that this is divisible by because it's a linear combination of things which are divisible by delta b of b. Okay, so this is if one is not in J, and if one is in J, then you remove the column J, so it's also true. Because there is no, you don't do anything when you make a linear combination here. Okay, since you can do that for any columns and also for any rows, you deduce that for any matrices U and W, delta B of B divides delta B of U, B, W. Okay, so I just made the computation for the first column of W, but then you can have a second one and so on. Okay, so hence, if U, B are invertible, if U and W are GLN over R, then you deduce that delta B of B is equal to the smallest common divisor of delta of UBW. So this notion of greatest common divisor is invariant by multiplication on the left and the right by elements, invertible matrices. So once you know that, you write if A is symmetric, A can be written as UD U star with D diagonal by the spectral theorem, and U star and U identity. So in particular, A minus X is equal to U D minus X U star. Okay, and so delta B of A minus X is equal to delta B of D minus X. Okay, so you have reduced the problem of computing delta B when the matrix is diagonal. And then that's pretty obvious how you get this formula for diagonal matrices. Because what you do is D is lambda 1, lambda 1, lambda 1, lambda 1, lambda 1, M1 times, lambda 2, lambda 2, lambda 2, and 2 times, 0, 0, okay, and so on. And so when you remove, if you remove B rows and B lines, maybe I should say that if it's the diagonal, Pij of D minus X is 0 if I is different from J. Because if I is different from J, you will have a columns of zeros. Okay, so you only have to consider the diagonal term, and when you consider the diagonal terms, if you take I to be the first B elements in the first, corresponding to the indices of eigenvalue lambda 1, you will obtain an exponent of you consider the corresponding determinant. You will have reduced the multiplicity in the submatrix of eigenvalue lambda 1 by B. And you can do that for all eigenvalues, and that's how you get this formula. It's a bit. I encourage you to try to write down that properly, but I think I've given you all the ideas. Okay, so once you know that, you can make the proof of the theorem. Okay, so the theorem is here. You have to find you have a minimal path matching from I to J, and you want to an upper bound. Since you know that this is exactly, now we have made some progress. We know that this is a degree of delta B. This is a degree of delta B. Okay. We want to prove that there exists a non-trivial polynomial of degree L in the collection Pij. Of course, what we will take to be I to be the subset of vertices in I, and J the subset of vertices in J. Okay, so the strategy is pretty obvious thanks to the notation. So you want to prove that the question is whether or not the degree of Pij of X yes, what was my notation? So, Pij of A minus X, Pij of A. Okay, maybe it's better to write it exactly what it is. The degree of A minus X I J, where I and J are these you want to prove that the degree of that is L. Okay? If you prove that, you will have proved the theorem. So it's more convenient to, so you have I, it's more, so I will assume that there is a unique matching map, maybe. A minimal matching, oh, we'll see that later. So I find more convenient to work with matrices of size n, because this is a matrices of size n minus b. Okay, so you define a matrix of size n that you obtain from that you build from A like as follows. You define Bij for B of EGL to be, we assume, okay, which is EIL. We assume that the matching map of minimal pass matchings is the identity. Okay, and so you define a new matrix which has so it's a direct mass. So you send the vector JL to IL. So here I have my set I, here I have my set J, and in the matrix B, you send GL to BL. Okay, so this is vertex JL. You send it, so there is an arrow, you send it to IL. Okay, and for J different from L, from J, B of delta J is equal to the sum over all I, not in I, of A, Ij, delta I. Okay, so, and then the matrix, maybe I change color. If you want to picture it, you put outgoing edges outside the elements of IL in B, and then all the other vertices are the vertices of A. Okay, so you just remove the ingoing vertices at A, and at all vertices of J, you put a virtual arrow between J to I. And if you do that, after a moment of thought, you define D to be the diagonal matrix, D diagonal matrix, with X is equal to 1 if X is not in I or J, and 0 otherwise. Okay, and if you look, you will observe that the determinant of B minus XD is exactly the determinant of A minus Xij that you are interested in. The point is that it's easier to work with B because it's an n by n matrix and it's clearly built on the graph. Okay, so then you expand and you use a formula of, I don't know, maybe. It's the signature, maybe epsilon to the tau, the signature of the permutation is the sum over all permutation in Sn of the product over all X of, maybe X is not good because X is already the parameter of my polynomial, B of X minus B of X D of V tau of phi. Okay, and so you can write that as a sum of all permutations of the signature of the permutation of some polynomial Q tau of X. Okay, now I claim that you can write that as a sum over all pi which are matching paths from I to j of something which will be the signature, which is minus 1, 1, times the determinant of b of x minus xd restricted to pi. Okay, where pi, the matching path is a collection of vertices. So here you remove, when you remove these vertices. Okay, so when you remove the vertices in pi, since when you are not in pi, the entry R1, you can put b minus x here. Okay, so why is that? You say, you observe that indeed, if qt of x is not 0, so if this polynomial is not 0, let's make a picture. Okay, so you have to, you take IL, okay, you have to find the tau. If this is not 0, since you have to put a 0, the diagonal term is 0, tau of v must be one of the neighbor of IL, okay? So if this is necessary, tau of IL will be one of the neighbor of IL, okay? And then tau of IL will be a neighbor of IL and so on. Then you will continue. At some point, you will reach an element of J, maybe not this one. Okay, I follow the successive iteration of, so this is tau squared of IL, tau cube of IL, and so on. And I arrive at tau power PL of IL, which is some element J of sigma L, where sigma is some matching. Okay, and I arrive here in J. And then when I am in J, I have only one possibility, because the diagonal term is 0 again. And here, the B term is only non-zero if I go to IL. So when I make an extra iteration, I will arrive here and repeat the process, okay? Until I have completed my loop. Okay, and so, and all the weights, but the entries of these are exactly 1. Okay, so here the entry, you have to take the product. When you take the, since when V is different from tau of V, this is B of, if V, this is simply B of V of tau V. If tau V is different from V, okay? When you are not a fixed point of the permutation. And so this is 1 or 0. This is 1 or 0. Okay, so these products, so there is this bunch of products of 1, which is here. And then what remains is precisely, so when you have made this union of permutation, so this you have exactly spanned a path pi, and what remains is a determinant of the submatrix. Okay, so that's the explanation of this formula. Okay, so there are more details in the notes if you are interested. And I should say that the determinant, that was the determinant, the degree of the determinant of b minus x pi pi, since this is I could put a b, this is the same thing as I could put an a here, because when I am outside pi, b and a coincide, okay? And the determinant of that, since a, the degree is exactly the length of pi, it's n minus the length of pi. Okay, so this is a polynomial, and the largest degree terms will be up. This is a this all terms is a polynomial, and the largest the largest degree terms will be contained for the minimal path matchings, which are the one which have pi, the length of pi, which is minimal. And now is the next trick, but there is a sign, there is a sums here, and the sum is signed because epsilon pi could be minus 1, 1. So there could be huge cancellation. But if all matching maps are equal, then there will be no signs. So let's assume, for example, if the minimal path matching is unique for simplicity, this will be written as minus x power L plus some lowest order term. If the minimal path matching times is not unique, you have to be sure, you have to be sure that this terms does not cancel. And so assume that the minimal path matching is unique for simplicity, so you deduce that the degree of delta B of, so the degree is L, so the degree of delta B of A is bounded by L. Okay, so this concludes the proof. So you have seen that the uniqueness of the minimal path matching is crucial to avoid some cancellation. And if you think about the Lamplighter group, this is exactly what happens. Now, we use this theorem in 1 minute. We apply this result for percolation on Z2. So what we do is we make a picture and stop here. We have some, so you make bound percolation on Z2. So I only keep some edge with probability P minus 1 minus P. I am supercritical. So P is above PC, the critical percolation. So I take a box of size N. I know that the atoms of this box of size N converge to the atoms of the infinite graphs by this Luke approximation theorem we saw last time. So it's enough to understand them. So what we would like to prove, we would like to, this is a set, this is a left part and the right part. Okay. And we would like to find a path in our graph, which goes from left to right, which are vertex disjoint. Okay, and which have a cardinality. So this will be the set of red points. This will be J. This is J, and this set is I. Okay, and what we would like, so the cardinal of I is the cardinal of J is B. And so the number, if we have some right-left crossing on the percolation graph, the length of the minimal path matching will be at most, so we'll assume that this number is at least epsilon n. The length of the minimal path matching is at least B times n minus, so the length of the minimal path matching is the total number of vertices, so it's at least B times n, okay, so which is larger than epsilon n squared. So the number which is okay, so what you can, so L, so this we wrote that as being n minus n squared minus L, so it implies that L is at least L, sorry, is at most n squared times 1 minus epsilon. Okay, so if you apply that, it implies that the sum of the multiplicities of any k multiplicities is bounded by the number of bad vertices plus L, which is n squared times 1 minus L, okay, which is bounded by, let's say, n plus n squared minus 1 vector 1 minus epsilon. So when you come back to, you normalize to this total size of the graph, you obtain that the sum of the multiplicities when you sum k vertices is bounded by 1 over n, k over n by the lemma, so it's k times b plus 1 minus epsilon. Okay, and you let when n goes to infinity, this goes to 1 minus epsilon, so it's strictly less than 1. So this is how we prove this percolation on Z2. And we use the fact that we can indeed find such minimal path matching by a general result of Kesten from the 80s. We just prove that you can find such collection of paths as soon as P is larger than PC. And the planarity is very important because this is due to the planarity that we know that there is a unique, the minimal path matching is unique. The unique minimal path matching. Okay, and in dimension 3, our argument does not work because we don't know that there is not this uniqueness of the minimal path matching. So that's why we cannot apply our result directly in Z3, for example, which is a pity. But okay, so this is sorry, I'm a bit late, and so this is the end of the 4th lecture, and we will have a last lecture on Monday. Thank you.